right, let's talk about the amazing power and flexibility of pneumatic and hydraulic systems. And isn't that amazing power to pull up that gear like that? Well, they're going to ask you a few questions about hydraulic systems. Figure you should know something about it, so let's take a look at some of those questions. One of the things they want you to know is that all fluids readily transmit pressure. Why is it fluids readily transmit pressure? Because fluids are incompressible, and therefore they transmit pressure readily. They're also going to ask you, what is the viscosity of a fluid? What does that mean? Well, viscosity is the internal resistance of a fluid. It tends to prevent it from flowing, slows it down quite a bit. What are desirable properties of a good hydraulic fluid? Well, they are low viscosity, chemical stability, they don't combine with other things, create chemical reactions, and high flash point. Now, flash point is when the fluid gives off ignitable vapors. You want that to occur at a very high temperature. And high fire point. Now, fire point is getting enough vapors to support flame. Those are desirable characteristics of a good hydraulic fluid. I would think so too. Now, when you're servicing hydraulic systems, you want to use the type of fluid specified in the aircraft manufacturer's maintenance manual or the service manual or the instruction plate affixed to the reservoir unit. In other words, you cannot go wrong doing what the manufacturer tells you to do. Now, let's take a look at the two most common types of hydraulic fluid currently found in aircraft. And by the way, hydraulic fluids are dyed a specific color for each type of fluid. So one fluid here is mineral-based, which is referred to as petroleum-based. By the way, petroleum is a mineral, and it is dyed red. So if you saw the fluid itself, you'd know it was dyed red. And the other is phosphate ester-based, which is Skydrol, and it's a synthetic, and it's dyed purple. Now, let's take a look at some information they want you to know. First of all, information about the compatibility of fire-resistant hydraulic fluid with aircraft materials can be obtained, once again, from the manufacturer's technical bulletins. So where do you get information about the compatibility of materials with hydraulic fluids? The manufacturer's technical bulletins. You cannot go wrong by using the manufacturer's information. Now, let's take a look at some of the pros and cons of these hydraulic fluids. First of all, petroleum or mineral-based hydraulic fluid, as you remember, is dyed red. Now, one of the cons, I would think, is that it is flammable. I can't think of why that would be a good thing, but one of the pros is you can use it with synthetic rubber, neoprene rubber, and Buna and seals. Now, the FAA wants you to know that additives have improved the properties and characteristics of petroleum-based hydraulic fluid through the years. Now, let's take a look at vegetable-based hydraulic fluid, which is mil-spec 7644. And these aren't used very much anymore, but they're dyed blue in color. They're flammable under normal conditions. And vegetable-based hydraulic fluid is used with natural rubber seals. And that's the reason it's not used much anymore. There aren't too many natural rubber seals around anymore. Now, as you already know, both petroleum-based and vegetable-based hydraulic fluids are flammable under normal conditions. Well, that's really not as good as it could be, so mankind, as mankind does, made an improvement with a synthetic hydraulic fluid called Skydrol, or more officially it's called phosphate ester-based hydraulic fluid. And that's a synthetic. It's dyed light purple, so you can tell it has a wide operating temperature range. But the most important thing, it's fire resistant. It has a high flash point, tremendous temperatures, and it doesn't catch fire. Now, packing materials made for ester-based fluids must be used when you're using this. An example would be butyl rubber seals. So not just any kind of packing materials, they must be made for it. And the biggest disadvantage of phosphate ester-based fluid is it's very susceptible to contamination from water in the atmosphere if you leave it unprotected in the atmosphere. However, it is compatible with or resistant to most common aircraft metals, and they say on the test and the official FAA materials, it's also compatible with polyurethane and epoxy paints. These are the ones that look wet all the time, really shiny. Well, I can tell you from experience that's not necessarily true, but it is the correct answer on the test. It's also compatible with natural fibers and also with nylon and polyester. So it's pretty good stuff, very flexible, high flash point, really great. But you cannot mix it. In fact, they're going to ask you a question about mixing hydraulic fluids. Let's take a look at that question now. Now, let's assume you have an aircraft system, a hydraulic system that requires mineral-based hydraulic fluid like 5606, and let's assume instead you use a phosphate ester-based fluid like Skydrol. The question is, what is going to happen? Well, the system will become contaminated because the fluids will not blend and the seals will fail. That's considered to be a very bad thing. Let's talk about hydraulic seals. Now, there are various kinds of seals. One kind of seal is an O-ring seal. Here's a good example of an O-ring seal. This is a cutout so you can see what it looks like. They're the most commonly used type of seal, and they're used to prevent external and internal leakage in aircraft hydraulic parts. Now, if the O-ring has a little blue stripe or a dot, it's to be used with mil-spec 5606 mineral-based fluid. So if you're going to use it with mineral-based fluid, it should be marked with a blue stripe or a dot. All right, let's talk about high-pressure O-rings. Now, let's assume you're going to operate an O-ring in a system having above 1,500 psi. Now, one of the problems you could have when you got very high pressure is that the O-ring actually gets squeezed by the hydraulic pressure until it's actually in between the moving and the stationary part. They call that extruding it. It gets extruded between the two. What do you do to prevent that? And the answer is you use a backup ring. There are special rings made to back up the O-ring to keep the O-ring from extruding between the moving and the stationary part. Now, where do you put the backup O-ring? Do you put it on the pressure side of the O-ring or on the side away from the pressure? And the answer is you put the backup O-ring on the side away from the pressure. That's where it would tend to be extruded through, so that's where you put the backup O-ring. Now, let's take a look at figure 12, and let's assume that you have a Teflon backup ring, and they're going to ask you to look at these three possibilities for Teflon backup rings, and they're going to ask you which of these spirals would be the correct spiral for a Teflon backup ring. Well, what you want to avoid is having any kind of joggle. You can see that spiral 2 would have a joggle, spiral 1 would not, spiral 3 would not. So illustrations 1 and 3 show the correct spiral for Teflon backup rings. Now, let's take a look at the difference between gaskets and packing materials. Now, gaskets are normally used in stationary parts, and packing materials are flexible sealing elements, seals, used when you're subject to motion. So, packing materials are flexible sealing elements, seals, subject to motion. And that's in between moving parts normally we're talking about here. Now, to protect packing rings or seals from damage when you're installing them over or inside threaded sections, they say if you're going to put this O-ring, we'll say an O-ring can be a packing material, by the way, over a threaded section, put a little cardboard on the threaded section, then put the O-ring on it, and you're just protecting the seal from the threaded sections. This should be covered with a stiff paper sleeve is what they say on the test. Now, let's take a look at some basic hydraulic information they're going to ask you on the test. First of all, they're going to ask you about Pascal's law. And here's a good example of Pascal's law. According to Pascal's law, pressure in an enclosed hydraulic system is equal and undiminished in all directions. In other words, if you have 100 pounds per square inch here, you've got it everywhere in the entire system. And that's the principle in which hydraulic systems work, and that's Pascal's law. Now, pressure is a term used to indicate the force per unit area. They're going to ask you this on the test. It's force per unit area, and it's expressed in pounds per square inch. So pressure is expressed in pounds per square inch. Now, let's assume you take a hydraulic system like this and you build up 100 pounds psi pressure, 100 psi pressure, pounds per square inch pressure. And let's assume the piston is 1 inch diameter. So you have a 1 inch diameter piston. Let's assume you have a 1/2 inch line, and you have an actuating cylinder. Well, here's the piston, is 1 inch diameter, 1/2 inch line, actuating cylinder, we'll say 2 inches in diameter. They're going to ask you the question, what is the pressure in the line in between the pump and the actuator? Well, if you have 100 psi anywhere in the system, you have 100 psi everywhere in the system, and it doesn't matter whether you have a 1/2 inch line, 2 inch line, 2 inch cylinder, 1 inch cylinder, it doesn't matter at all. If you have 100 psi anywhere inside the closed part of the system, you've got 100 psi everywhere, and that's what they're asking you on the test. All right, now, hydraulic systems in aircraft have certain characteristics. One of them is the minimum maintenance requirements, another they're lightweight, and others are simple to inspect, and that's why they use hydraulic systems in aircraft. Now, excluding lines, they're going to ask you on a test, what are the basic components required to make a simple hydraulic system? Let's take a look at it. First of all, you have to have a pump. And here we have a hand pump. You have to have a reservoir to supply that pump. We have that. Then you have a selector valve, so you can decide whether you're going to run it to the actuator or back to the reservoir. And finally, you have an actuator. So the simple parts of a hydraulic system, if it's a simple hydraulic system, are just those things right there: the pump, the reservoir, selector valve, and an actuator. Now, they're going to ask on a test, what is a hydraulic system referred to as a power pack system? Now, a power pack system is when you have the motor and pump all together as one unit, and they say that on the test as having hydraulic power components in one unit. The motor and the pump are all together. Now, let's assume you get air in a hydraulic system. They're going to ask you, is that normally a problem? And the answer is no. Removal of air from a hydraulic system generally presents no problem because the air will be removed by operating the various hydraulic components through several cycles. So air is not normally a problem in hydraulic systems. Now, they're going to also ask you a question about air. They're going to say, if the time required to operate a hydraulically actuated mechanism decreases with successive operations, what's that mean? Well, if in other words, if it operates better every time you operate it, operates faster, it indicates the air is being worked out of the system. Now, let's take a look at a few things the FAA wants you to know about hydraulic pumps. First of all, they want you to know there are two types of hydraulic pumps: constant displacement types and variable displacement hydraulic pumps. Let's take a look at a constant displacement type. And a constant displacement hydraulic pump is able to deliver a uniform rate of fluid flow. In other words, the same amount of fluid per hour per minute comes out of a constant displacement type. On the other hand, a variable displacement hydraulic pump is a current design, and it contains a built-in means of system pressure regulation, and it can vary the amount of fluid that it delivers. And that's the difference between the two. Now, the FAA wants you to know a few things about pump malfunctions, so let's talk about how a pump functions before we talk about how it malfunctions. First of all, here's a hand hydraulic pump, very simple. This piston is connected to a handle, and you move the piston back and forth. And when you move the piston to increase the size of the cylinder here, what happens is hydraulic fluid flows from the reservoir through this check valve into the hydraulic cylinder. And this is a check valve that allows the fluid to flow in but not out again. That's the input valve or import valve. Then when the piston is all the way in the far end of its direction there, travel, then what you do is push back on the piston. Now, this check valve won't let the fluid go this direction, but this check valve is the output valve, lets the fluid go out, but it won't let the fluid return. So you have two check valves. One lets it flow in, the other lets it only flow out, and that's a very simple hand pump. Now, they're going to ask you a question about a malfunction of this pump. They're going to say, if the handle of a rebuilt hydraulic hand pump cannot be moved in the pumping direction. In other words, you can pull it out, but you can't push it back. It can't be moved in the pumping direction. What's likely to be the problem? And the answer is you might have installed this check valve backwards here such that it won't let the fluid out. So one example, one possibility is an incorrectly installed hand pump outport check valve, probably installed backwards. All right, let's take a look at another question they might ask you about this. They're going to say, let's assume you're operating this pump, a hand pump like so, and you have severe kickback. And by the way, this could be an emergency hydraulic pump. That's what this would be right here, just a hand pump. What would that severe kickback indicate? And the answer is it indicates the hand pump outport valve is sticking open, because what happens is if this valve sticks open here, this check valve, it lets the fluid come back and kicks back against the handle. So hand pump outport valve, check valve, is sticking open if you have severe kickback. And those are the couple questions they're going to ask you about hand pumps. Now let's assume you have a mechanical, not a hand pump, but a powered pump, electrical powered pump, and you have chattering of the hydraulic pump. What does that mean? Well, chattering of the pump is generally an indication of air in the system, and it could be caused by a leak in the pump inlet. That's generally the case, pump inlet leak. Now let's see if you and I together can figure out a more complicated hydraulic system. Here's a little bit more complicated one. We're going to use this as a model throughout the rest of the course here about hydraulics, so let's take a look at it real quick. First of all, you and I have a hydraulic reservoir, and then we have the hydraulic pump here. We could be having a gear pump here, some way to increase the hydraulic pressure. Then you have a regulator or an unloading valve that when the pressure gets high, it unloads the pressure and sends it back to the reservoir directly instead of through the hydraulic system. Then after you go through the regulator, you have here the accumulator. An accumulator has air on this side, hydraulic fluid on this side. Now, one of the principles of hydraulic fluid is hydraulic fluid cannot compress. It's incompressible. But air is compressible, so if you have this accumulator, as you increase the hydraulic pressure, it compresses this air. It's kind of a way of storing energy. It stores hydraulic fluid. When a pump gets overloaded and is delivering all it can deliver and you still need more, this accumulator can move this piston down and release some more hydraulic fluid into the system. So it's kind of a way of storing hydraulic fluid and storing energy. It's called the accumulator. Then you'll have actuator valves, and you turn the actuator valve and operate this system here with the actuator valve, and what's left over goes back to the system, or what's being returned will be returned back to the reservoir. And then you'll have a pressure relief valve here in the system somewhere over here like so. So here's a pressure relief valve. Now, a typical question they might ask you about this, they'll say, well, a hydraulic pump of the correct capacity, and you have a hydraulic pump here, and it has the correct capacity, but it fails to maintain normal system pressure during the operation of, we'll say, a cowl flap actuating unit. So let's assume that one of these actuators is actuating the cowl flap actuating unit, and you have the proper hydraulic pump, but it cannot maintain hydraulic pressure. What's the probable cause? Well, if you can't maintain hydraulic pressure, you have the proper pump right here, you might check for a restriction in the pump outlet. Let's you and I take a look and see why that might be a problem. First of all, you have to know where the pressure gauge is, and that's the important part of this. You have to know where the pressure gauge is. The pressure gauge is normally after the accumulator and before the actuator. And so if you can't maintain pressure here, it probably means that you're not getting proper flow out of the pump. You're just not getting it out of the pump, period, and you should check for that restriction in the pump outlet. Now, so where is the gauge normally? After the actuator, or after the accumulator, before the actuator, like so. Now, let's say you have a worn hydraulic pump shaft seal. So you have a hydraulic pump, and the hydraulic pump turns on a shaft, and there's a seal there is worn. Well, obviously what's going to happen is you would have hydraulic fluid leaking. So how would you detect a worn hydraulic pump shaft seal? Well, you detect that by hydraulic fluid flowing from the pump drain line. Normally you would have a pump drain line, and hydraulic fluid would get in there, and that would tell you you have a worn hydraulic pump shaft seal. How about that? You really wanted to know that, didn't you? All right, now let's assume you have a hydraulic system control and relief valve unit, and they failed to function properly. That's this hydraulic control and relief valve unit fails to function properly. How do you keep this pump from overpressuring? If your relief valve unit or a control valve unit fails, how do you keep the pump from just having too much pressure? Well, let's take a look at it. The way you keep it from having too much pressure is that you have a shear section on the main hydraulic pump drive shaft. In other words, if all fails to work properly, the relief valves don't work, the pump itself is protected because the drive shaft will have a shear section, and it will shear itself off, and you protect the whole system from blowing something up. The shear section or shear pin on the shaft of an engine-driven hydraulic power pump allows that shaft to break to protect the pump from overload if the pump should seize. All right, let's talk about pressure regulators. Now, a pressure regulator in a hydraulic system, and it was just after the pump if you remember there, is used to maintain system operating pressure within a predetermined range. And the way it works is normally you'll have a spring and a ball system, and if the pressure gets too low, it'll allow the pressure to build up in the system. If it gets too high, it bypasses, and that's the whole idea. So the pressure regulator also relieves the pump of its load when no actuating units are being operated. So it relieves the load and sends the fluid back to the reservoir, and that's the whole idea of the pressure regulator. Now, if the pressure regulator of a hydraulic system using a constant displacement pump diverts the fluid from this system to the reservoir, the output pressure of the pump decreases and the volume remains the same because it just simply allows it to flow back to the reservoir. So it does regulate the pressure, but it does not regulate the volume of the fluid, and that's what they want you to know on the test. Now, the pressure regulator in a hydraulic system with a constant delivery pump allows circulation of the fluid when no demands are made on the system, and that's the answer to an actual FA type test question. Another term for this pressure regulator is an unloading valve, and it's used with the hydraulic pump to relieve pump pressure. So it's called an unloading valve. Now they're going to say on all types of pressure regulators, is any attention required from the pilot? And the answer is on the spool type, any other type of hydraulic system regulator, they're automatic and they require no attention from the pilot or flight crew. So that's one thing you don't have to pay attention to as a pilot. Now if it's necessary to adjust several pressure regulating valves in a system, if you have a lot of pressure regulating valves in a system, the procedure is to adjust the one with the highest pressure settings first, because you want to adjust each one of them at its own highest pressure setting. So adjust the one with the highest pressure settings first if there's several in a system. Now they say, let's assume you want to remove a spool type or a balance type pressure regulator from a hydraulic system. What precautions should you take? And the answer is actuate some actuator, maybe the flap selector valve, until no pressure remains in the system, because remember, the accumulator can keep pressure in the system, and so you want to, before you remove any components in the hydraulic system, bleed the pressure off the system by operating an actuator. Trying to empty the accumulator is what you're trying to do. Now, they're also going to ask you a question about what is a restrictor in a hydraulic system. Well, a restrictor is any kind of restriction in the system to slow the flow. What is the purpose of a restrictor? Well, the purpose of a restrictor is to control the rate of movement of hydraulically operated mechanisms, and you just do that by putting a restriction in a line somewhere. It's called a restrictor. Now let's you and I take a good close look at a hydraulic accumulator. And this is a close look at a hydraulic accumulator. It says hydraulic accumulator, inflate to 600 psi. Well, let's take a look at a hydraulic accumulator inside the system and see what we have. Well, here's the system. We have a reservoir which supplies hydraulic fluid to the pump, and then a pump, of course, increases the pressure and sends it down the line. And then we have the accumulator. Now, the accumulator has either a piston or a diaphragm, and on one side of the piston or diaphragm is hydraulic fluid, and on the other side is air. Now, the purpose of this accumulator is to store or release energy, and here's how it works. See, the neat thing is air is compressible. It will compress and it will expand, whereas hydraulic fluid is not compressible. It will not compress and expand. So if you want to store some energy, you can pump air to this side of the accumulator and have hydraulic fluid on this side. And if you have too much pressure, what happens is you actually wind up storing fluid because you compress the air, and the excess hydraulic pressure goes into the accumulator. If, on the other hand, the hydraulic pressure begins to drop down a little bit for some reason, then the air shoves the piston this way or the diaphragm this way and releases some of the energy it's stored up here in terms of compressed air. Now, why would you want this hydraulic accumulator in here? Well, let's assume that you're pumping along, you're pumping fluid, you've got one of these controls activated, and all of a sudden somebody shuts it off, and the pump keeps on operating. There will be a great big pressure surge which will rattle throughout the entire system unless you have an accumulator. Because if you have an accumulator, what's going to happen is this hydraulic fluid will go into the accumulator. The increased pressure will just simply push this piston back this direction here, and by compressing the air, you'll store that energy and get rid of that surge. Now let's assume you open up a whole lot of devices here and you've got a need for a whole lot of hydraulic fluid, but you exceed the pump capacity. The pump is putting out all it can put out. Then the hydraulic accumulator comes into play one more time, because as the pressure begins to drop, this compressed air will force the piston or the diaphragm in this direction and will make up for that fact that the pump isn't putting out enough fluid, and it will temporarily supplement the system pump when demand is beyond the pump's capacity. Or you could actually have the pump completely fail, and for some period of time the accumulator will still keep pressure on the system. So there are three things this hydraulic accumulator does. They are, number one, it dampens pressure surges in the system. Number two, it'll supplement the system pump when the demand is beyond the pump capacity. And number three, it can store power for limited operation of components even if the pump is not operating. Another thing you need to know is a fully charged hydraulic accumulator provides a source of additional hydraulic power when heavy demands are placed on the system, so it's a wonderful device. Now, to determine the air pressure charge in the accumulator, If the engine is inoperative, but the system still has hydraulic pressure, there is a procedure you can follow. What you want to know is what is the air pressure here in the accumulator. We're assuming, of course, we don't have a gauge right here, but we have a gauge on the hydraulic side somewhere. There are some systems you can actually read the air pressure inside the accumulator. All right, but if you don't have a gauge there, here's what you do. You operate some hydraulic units slowly. Then note the drop on the pressure gauge. Remember, the pressure gauge is on the hydraulic side of the system. And note the point at which you get a rapid drop in pressure. Now, what's going to happen is the pressure is going to stay about the same as the air pressure until all of a sudden this piston will hit the stop here, hits the limit, and then all of a sudden the hydraulic pressure is going to drop off precipitously. Well, that pressure just before the rapid pressure drop is the pressure inside the accumulator. And once again, this assumes the pressure gauge is on the hydraulic side of the accumulator. So what you do is just simply operate some actuator until you get a rapid drop, and the pressure before that rapid drop was the pressure in the accumulator, and that's because the piston bottomed out there in its travel. So you take a look at this accumulator, you notice the air charge should be inflated to 600 psi. So once again, here's the way the FAA is going to ask you the question on it. They're going to say, to check the air charge in a hydraulic accumulator, reduce all hydraulic pressure, observe the reading of the accumulator air charge, and that's just before you get the rapid drop. Now, let's take a look at that accumulator again and talk about something else. You notice that you have this barrier between the hydraulic fluid side and the air side of the accumulator, and of course that's necessary, and that prevents air from entering the fluid system. And it physically separates the air chamber from the oil chamber, and it could be done with a piston or a flexible or moving separator, something of that sort right there. Now, let's assume that you kind of depress the core valve, the air core valve, or often called a Schrader valve here, to drain some air out of here. And when you do that, you get hydraulic fluid. What does that mean? Well, if hydraulic fluid is released when the air valve core of the accumulator is depressed, it's evidence of a ruptured diaphragm. It means that there's a leak here and you're getting oil in the air and air in the oil. Now, let's assume that a hydraulic accumulator has been installed and the air chamber has been charged. Now, what's going to happen is the main system hydraulic pressure gauge, which is on the hydraulic side of it, will not show a hydraulic pressure reading until the fluid side of the accumulator has been charged. That means you won't get any pressure on this side until you got the piston away from its stops. Then these two will be equal to each other. But when the piston's on a stop, either one stop or the other, then they won't be equal to each other. Now, they're going to ask you another question about this. Let's assume you have a hydraulic accumulator and you charge it with an air preload on the air side of 1,000 psi. There you go, an air preload of 1,000 psi. And you then develop a hydraulic system pressure of 3,000 psi. The question is, when you have moved this piston off the stop and now you have a hydraulic system pressure of 3,000 psi, what will be the pressure on the air side of the accumulator now? And the answer is, it'll be 3,000 psi. When the piston is off its stops, or the accumulator is off the stops, these two will be equal to each other, even if it was only charged with 1,000 to begin with. All right, if an aircraft's constant pressure hydraulic system cycles more frequently than usual, and no unusual fluid leakage can be detected, what would this tell you? And the answer is low accumulator air preload. What that means is if you have very little airspace in here, the pressure will build up very rapidly because this piston will hit its stops on this end, and you'll have the hydraulic system relief valve work, not work, relief valve work, not work. So one of the things the accumulator does is give you space to operate in here without having the system cycle on and off all the time, and that's the whole idea. If the hydraulic system pressure is normal while the engine-driven pump is running, but there is no pressure after the engine has been shut off, what does that indicate? And the answer is no air pressure in the accumulator, which may be caused by a leaking accumulator air valve. So if you had no air pressure in the accumulator, then there would be no pressure after the engine has been shut off because there would be no air here to expand and keep the pressure on there. Now, what would cause a loud, I should say, hammering noise in a hydraulic system having an accumulator? And that generally a loud hammering noise usually indicates too low or no preload in the accumulator. Same thing is happening. You're getting hydraulic hammering in here, and the accumulator is not allowing room for the hydraulic pressure, in a sense, to be relieved here, and it's relieved in part by the accumulator. Now let's assume, once again, you want to remove an accumulator or any part of a hydraulic system from the system. What do you first do? And the answer is you first relieve system pressure. If you want to remove any component of this hydraulic system, you better remove system pressure, and you do that by operating an actuator valve. Now, when hydraulic systems operate at high hydraulic pressures and high rates of hydraulic fluid flow through them, that causes an increase in the hydraulic fluid temperature. And for that reason, sometimes you have to put in a heat exchanger. So heat exchanger cooling units are required in some aircraft systems due to the fact that the hydraulic fluid gets hot. Now let's take a look at a relief valve in a hydraulic system. Here's a good example of a relief valve. A relief valve, of course, is to keep the system from over-pressurizing and causing damage, so at some particular point, and you can adjust the point, you relieve the pressure. Now there's another valve you need to know about, and that's called the power control valve. And a power control valve is used in simple hydraulic systems, and when you turn the power control valve, the hydraulic pressure goes up and the actuator works. When the power control valve is turned the other direction, the pressure does not build. Well, if you wanted to adjust the pressure that the relief valve pops off at, would you have to have the hydraulic control valve in the open or closed position? And the answer is the power control valve, they call it the power control valve, should be in the closed position to adjust the relief valve. Now let's you and I take another look at our complicated hydraulic schematic here. Here's the relief valve over here in this corner like so. And the other valve that we had that did a similar function was called the regulator, which was right here, or sometimes called the unloading valve. Well, if you want to adjust this relief valve, you've got to eliminate the action of the unloading valve, because the unloading valve will unload the pressure before the relief valve does. So they ask you a question about this, and the question goes like this: before adjusting the release valve of a hydraulic system, eliminate the action of the unloading valve, and that makes an awful lot of sense. Now, there is another valve you could have in here, and that would be the thermal relief valve. And if it's installed in a hydraulic system, it'll have a higher pressure setting than the pressure relief valve, than the main system relief valve, or the pump unloading valve. It'll be the highest pressure of them all, because that's for when your airplane's sitting on the ground and pressure builds up due to heat. The thermal relief valve has the highest pressure of them all. Now, let's assume you have a flap overload valve. What would that be for? And the answer is to prevent the flaps from being lowered at airspeeds which would impose excessive structural loads on the flaps. And it's just a valve that has you not have too much hydraulic pressure going to the flaps so you don't damage the flaps. It relieves instead of damaging the flaps. Now let's take a look at some other valves, selector valves, check valves, things of that sort. We talked about some of these briefly. The check valve in a system allows one-way flow. So on the FA test, you need to know the check valve allows free fluid flow in one direction and no fluid flow in the other direction. That is a check valve. Now, check valves are used in both hydraulic and pneumatic systems, and there is such a thing as an orifice check valve. Now, let's keep it clean. Let's take a look at an orifice check valve. In an orifice check valve, fluid flows freely in one direction, but the valve restricts the rate of fluid in its flow in the other direction, so that it's freely in one direction, slow in another direction. Here's a good example of a selector valve. They're going to ask you on the test, what is a selector valve used for? Well, in FAA talk, a selector valve is used to direct pressurized fluid to one end of an actuating cylinder and simultaneously direct return fluid to the reservoir from the other end. And that is the purpose of a selector valve. Aren't you glad you don't talk like that all the time? Well, a four-port closed center valve is one of the most commonly used selector valves, and it provides for simultaneous flow of fluid into and out of a connecting actuating unit in a hydraulic system. That's a four-port closed center valve. Now, one distinguishing characteristic of an open center selective valve selector valve used in a hydraulic system is that it allows fluid to flow through the valve in the off position. Open center type, as you remember, has no pressure on it until you close it. Then it goes through the actuator. Otherwise, it goes right through the open center valve. Now, they're also going to ask you, what is a hydraulic fuse? Now, hydraulic fuse is really a very, very clever thing. And it works like this. You have hydraulic fluid that normally gets to flow through this situation and all the way through. But if, for instance, there comes a rupture in a line over here, now you would like to stop the fluid from going through that ruptured line. So what happens is when the fluid starts moving at too fast a rate, it moves this piston into another position which covers up a hole. Then it stops the fluid from going through, and that's called a hydraulic fuse. And it's incorporated in some hydraulic systems to allow a normal fluid flow in the line, but it closes if the flow increases above an established rate, and that's called a hydraulic fuse, and it's just a gorgeous, gorgeous thing. All right, let's take a look at reservoirs. The main purpose of a pressurized reservoir, and here's a good example of a reservoir right here, the main purpose of a pressurized reservoir in a hydraulic system is to prevent hydraulic pump cavitation. Now, a pressurized reservoir is used in an airplane that flies at very high altitudes. Normally, it's air pressure that forces the fluid to the pump from the reservoir, and you go to very high altitudes, there's very little air pressure, so you need to pressurize the reservoir to prevent cavitation of the pump in order to keep from foaming in the reservoir. Now, if the hydraulic reservoir is pressurized with turbine engine compressor bleed air, an air pressure regulator is used to reduce the air pressure between the engine and the reservoir. So you've got to regulate the air pressure that goes into a pressurized reservoir. Now, before removing the filler cap of a pressurized hydraulic reservoir, it's a good idea to relieve the air pressure so you don't blow your head off. It's a wonderful idea to make sure you relieve the pressure. Now, let's take a close look at a hydraulic system reservoir. And if we go even closer and backlight it, what you'll see in there is a standpipe. And that standpipe gives you an emergency source of hydraulic fluid in case the reservoir itself develops a leak. You still have the fluid left in the standpipe. Now, that standpipe is located at the outlet of the reservoir itself or the inlet of the main system pump. So in the event you have a leak in the reservoir, this standpipe still gives you a supply for the main system pump. Now, there is another provision for problems because some reservoirs contain a small quantity of fluid which is not available to the main system pump, and that goes to the auxiliary pump. So with this kind of redundancy, you've got a backup for all sorts of contingencies. Now, if during a hydraulic system operational check, the wing flaps, for instance, cannot be lowered using the main system. Here's an airplane that might use a hydraulic flap system. If you cannot lower the wing flaps using the main system, but you can lower the flaps using the emergency hand pump, what does that tell you? And the answer is you probably have low fluid level in the reservoir, and you're only getting fluid from the auxiliary system or the standpipe. Now, let's assume you want to add fluid to a hydraulic reservoir. Now, the FAA asks you a question about this, kind of a weird sort of way. They say, let's assume it's a constant pressure hydraulic system, and you're adding fluid while the system is pressurized. Well, let's take a look at what's going to happen here. Here is your fluid, here's your pump, and when the system is pressurized, the fluid goes into the accumulator. This is a nitrogen charge, and as the system is pressurized, the fluid fills up this accumulator, compressing this nitrogen charge, making less room for the nitrogen and more for the fluid. Now, let's assume at this point, when you have the fluid system pressurized, you add fluid to the reservoir. Then you unpressurize the system. What's going to happen? Well, the pressure is going to come off, the nitrogen charge will expand and drive the fluid back out of the accumulator and fill up the reservoir even further. Well, now what's going to happen then is if you had this reservoir very, very full, you could now overfill the reservoir. So you always want to make sure that you follow the manufacturer's instructions when you're adding fluid to a hydraulic system. And on the other hand, however, if you have an inadequate supply of fluid, that will cause what? Well, if you had an inadequate supply of fluid, it's most likely to cause excessive fluctuation of the pressure gauge when the hydraulic pump is operating. So if you see An excessive fluctuation of the pressure gauge when the hydraulic pump is operating probably would tell you that you have an inadequate supply of fluid. Now, they're going to ask you some questions on the test about hydraulic actuators, and one type of hydraulic actuator is a hydraulic actuating cylinder, and they're going to ask you what is the purpose of that cylinder. Well, the purpose is to transform fluid pressure, which is hydraulic pressure, into linear motion so that you can do useful work. Now, these words are important. We're talking about fluid pressure transformed into linear motion so that you can do useful work. Now, another kind of hydraulic actuator is a hydraulic motor, and it converts fluid pressure to rotary motion. So a hydraulic motor converts fluid pressure to rotary motion. One type of hydraulic motor is a piston-type hydraulic motor, but any hydraulic motor has an advantage over an electric motor. What is that advantage? No fire hazard if the motor becomes stalled. So that is a great advantage. No fire hazard for hydraulic motors. Now, if you have two actuating cylinders which have the same cross-sectional area, but have different lengths of stroke. Here's two hydraulic cylinders, same cross-sectional area, different lengths of stroke. Now, and they're connected to the same source of hydraulic pressure. The question is, will they exert different amounts of force or equal amounts of force? And the answer is, if they have the same cross-sectional area, they'll exert the same amount of force. And will they move at the same rate of speed or different rates of speed? And because it's the same cross-sectional area and the same amount of fluid per minute enters this area, they'll move at the same rate of speed. You might guess there's going to be another question coming about this. Let's assume you have two hydraulic actuating cylinders, and we do right here, which have the same length of stroke. They have the same length of stroke, but they have different diameters. They have different diameters, and they're connected to the same source. Will they operate at the same or different internal pressures? Well, remember the law, Pascal's law. If you have 100 pounds here, you have 100 pounds there, you have the same internal pressure if they're connected to the same source everywhere, but they will exert different amounts of force because the cross-sectional area. If you have 100 pounds per square inch of force and you have more square inches, you're going to exert more force. So they will exert different amounts of force. They'll have the same internal pressure, but they'll exert different amounts of force. They're going to ask you on a test also, what is a shuttle valve? Well, a shuttle valve is a hydraulic component which directs fluid from the normal source or an emergency source to an actuating cylinder. In other words, it chooses between the normal source and the emergency source, shuttles back and forth, and it directs the fluid to a hydraulic cylinder. For example, a shuttle valve is used in the brake actuating line to isolate the emergency brake system from the normal power brake control system. It isolates emergency from normal brake systems. They're also going to ask you, what is a cross-flow valve? Well, that's designed to bypass fluid from one side of an actuating cylinder to the other side, and it's installed in the landing gear system on some aircraft. The cross-flow valve smooths or cushions the rate at which the landing gear goes down. It doesn't let it drop down. It forces fluid to go from one side of the actuating cylinder to the other side to slow the gear down. That's called the cross-flow valve. Now, a common cause, by the way, of slow actuation in any actuating unit is internal leakage in the actuating unit. This fluid is leaking past some seals, and therefore it's not doing its job, and it causes slow activation. You recognize this, don't you? It's a filter. It's not what the FAA calls it. The FAA calls it a hydraulic fluid filtering element. They're constructed of porous paper, and the FAA wants you to know they're normally discarded at regular intervals and replaced with new filtering elements rather than being cleaned. Let's take a look at a micronic filter. A micronic filter is a filter incorporating specially treated cellulose paper. The FAA wants you to know a few things about lines and tubing. For instance, let's assume that you have Teflon hose that's been exposed to high pressure or temperature, and it's developed a permanent set. The shape is set into it. Now, should you change that set? And the answer is no. Teflon hose that has a permanent set should not be straightened or bent further. If for some reason you remove it temporarily, you should put it back so that it has the same shape. You do not want to change that permanent set. All right, let's take a look at hydraulic hose. Hydraulic hose identified as mil spec 8794, the FAA wants you to know, will have a yellow stripe. In reality, it has yellow lettering like this, running the length of the hose, and that stripe is used to ensure that the hose is installed without excessive twisting, because the lettering would be twisted. All right, now let's assume that you have an open end of a hydraulic line. You'd like to protect it from contamination. How would you do that? Well, you do it by sealing the lines with caps or plugs. And here's a good example that protects it from contamination. Now, let's assume that you are installing metal hydraulic lines like these right here. Well, what the FAA wants you to know is that you should put bends in the lines. That's actually a good thing, because that will allow the tube to expand and contract with temperature changes, and bends also absorb vibration. Now, let's assume that you're installing a rigid tube up here to a fitting, and as you're doing it, the flare just won't quite reach the seat. Is it legitimate, the FAA wants you to know, is to use this nut and pull it on? And the answer is no, you can't do that by tightening the nut, because you might wind up distorting the flare here. All right, now, can you have dents in a hydraulic line? How about in a bend? And the answer is no, you can't have dents in a bend or the heel of a bend. Now, dents in general are acceptable according to these rules. They're acceptable if they're not on a bend and they're less than 20% of the tube diameter. Man, that's going to take some careful measuring, isn't it? Let's talk about hydraulic fittings, and here's a couple real good examples of hydraulic fittings. These are quick disconnect couplings, and what they are is couplings that allow you to take the line apart without losing hydraulic fluid or letting air into the system, and they use them for hydraulic pumps very often, so you can take the pump out of the system and inspect it real quickly and do it without introducing air to the system or losing fluid. Now, the FAA is going to ask you a question about it, so let's cover it exactly the way the FAA is going to ask you about it. They want you to know that quick disconnect couplings provide a means of quickly connecting and disconnecting hydraulic lines without loss of fluid or entrance of air into the system. Now, let's take a look at figure 11, and let's take a look at another question about hydraulic fittings. And the question is, if you look at 1, 2, 3, and 4, you see all of these. First of all, which of these are flared type fittings? And the answer is 1 and 2 are flared type fittings. You can see by the bevels up here. 3 and 4 are not flared type fittings, because 3 and 4 don't have the bevels. Now, of the flared fittings then, the follow-on question I want to ask you, and we'll get the answer to what the FAA is looking for here. The follow-on question is, which of these is an AN type fitting? And the answer is number 1 is an AN type fitting, and you can tell that because the threads don't go all the way to the nut in the center, and you can look at the bevel if you're experienced and see that that's an AN type. Number 2 is an AC type fitting. Now, they're going to ask you in the test which of these is an AN flared type fitting, and the answer is number 1, and you look at the threads, they don't go all the way to the nut, and then you look at the bevel, and of course that tells you it's a flared type fitting. Now, let's assume you're having an extremely hard day. Now, that'd be hard to understand, but it's possible you're having a difficult day. And let's assume you service an aircraft hydraulic system with the wrong fluid. What do you have to do about it? The answer is you're going to have to drain the system, flush it, and usually you're going to have to change all the affected seals. Now, to flush the system normally serviced with Skydrol, you would use trichloroethylene. So if the system normally is serviced with Skydrol, flush it with trichloroethylene. Now, let's assume that you have a hydraulic system that uses Skydrol, which, as you remember, is phosphate ester-based hydraulic fluid. Now, let's assume that you want to clean the outside of components in this system, and the components are things like installed pumps, lines, and actuators. What could you use to clean those components? And the answer is you could use Stoddard solvent. It's only if you want to flush the inside of the system that you have to use the less handy trichloroethylene. By the way, do not confuse carbon tetrachloride for trichloroethylene. Carbon tetrachloride has been discovered to be toxic. You wouldn't want to clean anything with that. How about mil-spec 5606 systems? If you have a system that normally takes petroleum-based 5606 hydraulic fluid, you'd flush that with naphtha or Varsol. Now let's you and I take a look at pneumatic systems. Now one advantage people claim for pneumatic power systems is that no return lines are required. You're using air as the medium, you don't need to keep it, it's not particularly valuable, so you exhaust it or dump it overboard. Hydraulic fluid you want back, air you don't need back, so in pneumatic systems you do not need a return line. Now, the FAA wants you to know that relief valves are used in pneumatic systems as, and this is FAA talk, damage preventing units. That's a relief valve in a pneumatic system. Also, they'll ask you about the absolute pressure regulator. To understand it, you need to know that pneumatic systems normally are used on jets or turbojets. They use bleed air off the compressors, and then you have an air compressor that further compresses the bleed air. Now you want to regulate the air going to the compressor, so absolute pressure regulators regulate the compressor inlet air to provide a stabilized source of air for the compressor, and that's the absolute pressure regulator. Also, you have to have a moisture separator regardless of what kind of compressor you're using. So a moisture separator is required on a system which incorporates an engine-driven multi-stage reciprocating compressor, and the reason you need a moisture separator is to prevent freezing at the actuators. Also, you have a solenoid dump valve in a pneumatic system, and a solenoid dump valve is supposed to actuate and vent accumulated water when the pressure or the compressor shuts down. But if you have a malfunctioning solenoid dump valve, that will cause the moisture separator to not vent accumulated water when the compressor shuts down. The FAA turns these things around backwards for you. Well, believe it or not, you and I have covered everything the FAA wants you to know about hydraulics and pneumatics on the Airframe written exam.